SwayamPrabha. Digital India. Educated India.
We shall start our discussion today on the simple Rankine cycle, and we will discuss about the problematic issues which are involved with the cycle, and then we shall go to discuss about the modifications of the Rankine cycle essentially towards the increase of the efficiency of this particular cycle. So, you know that in the last class we have discussed about the simple Rankine cycle, and we could establish the efficiency of the Rankine cycle in terms of the heat which is added to the cycle and the amount of heat which is rejected from the cycle. Before going to discuss about the design modifications of this particular cycle, it is essential to understand first what are the issues, in particular the problematic issues involved with the cycle, and only then we can look for remedial measures towards addressing those issues for the enhancement of the cycle. It would be wise to again draw the simple Rankine cycle schematic diagram of the vapor power steam power plant, and then we shall go to discuss about the problematic issues. So, in the last class, so this is the boiler, this is the turbine, we are getting work output, and this is pump where we need to provide work input. So, this is Q in, and after doing work steam is taken to this mechanical device, that is condenser, and steam, that is the working substance in this part of the cycle, that is the low temperature part of the cycle. So, this is Q out. We collect condensate and it is again pumped back to the boiler. So, now this is a closed cycle. So, if we try to describe all the processes by comparing them with the Rankine cycle, then we had drawn this TS diagram in the last class, that is so this is P condenser and this is P boiler. So, this is basically the TS diagram of ideal simple Rankine cycle. We also discussed about the corresponding PV diagram and also HS diagram. So, let me draw the PV diagram today, because it is very important. So, this is the corresponding PV diagram. Though I have used several points 1, 2, 3, 4 in the TS and PV diagram, it is essential to mark those points in the schematic. So, this is 1, this is 2, this is 3, this is 4. Now, what we have discussed in the last class, that in this cycle, if we compare this TS diagram with the TS diagram that we had seen for the ideal Carnot cycle. So, this 2 to prime, this additional part. So, the total heat addition here is at the constant pressure, that is at boiler pressure. So, this segment 2 to prime, that is the sensible heat transfer, is the additional feature that we can see from the TS diagram in the frame of this Rankine cycle. So, and if I can recall, probably I discussed that it is because of this segment of heat addition. I mean, this particular segment lowers the temperature, average temperature at which heat is added to the cycle. So, you know that if I try to mark here, so that is the this is the high temperature part of the cycle, and this is low temperature part of the cycle. This segment 2 to prime, it lowers the average temperature at which heat is added in the high temperature part of the cycle, and it is because of this reason the efficiency of the ideal simple Rankine cycle is less or lesser than the efficiency of the ideal Carnot cycle. So, at least we have identified that this particular segment, that is 2 to 2 prime, that is sensible heating, which lowers the average temperature at which heat is added in the cycle, of course in this high temperature part of the cycle, right. And we can understand. So, this is the reason for which the efficiency will be lesser. So, let us quickly revisit the mathematical expression of the efficiency of the Rankine cycle. What is that? Just by looking at the heat addition and heat rejection. So, you know that heat is being rejected. So, if I mark over here, so this is the portion which represents the amount of heat which is rejected. As I told you, area under the process line in the TS plane is the indicative measure of the amount of heat transfer, whether it is transferred to the system or from the system. So, this is Q out, and heat addition is the area, we can say if we give name, this is A and this is B. So, I am not going to mark the hatched portion. So, the area under A 2 2 prime 3 B, that would be the heat addition, and heat rejection area under the portion, area of the portion, that is A 1 4 and B, right. So, if we subtract these two, we will be getting W net. So, what is W net? W net is, this is W net. Okay. So, this is the W net. Let me write here. Okay. If we can express these two quantities in their specific forms. So, you know that what we can write is that, so the cube 2 3, that is H 3 minus H 2, and cube 4 1 minus H 4 minus H 1. So, these two expression we can write easily by applying the first law of thermodynamics to a process which is steady state steady flow process. So, these two are, I mean the expression of these two quantities, that is heat addition and heat rejection. So, if I write here, so this is heat addition and this is heat rejection. So, what would be? So, we are applying obtained by applying first law to a steady state steady flow process. And then we can write it a thermal Rankine equal to W net by Q in, and what is W net? Q in minus Q out divided by Q in. So, these are small specific quantities, 1 minus Q out by Q in, right. I am not going to write the expression of work that is added to the system and the expression of work that is coming out from the system. So, you know this quantity should be, I mean if we write in the specific form, so it should be W. So, if we write it that small w out will be equal to H 3 minus H 4 and small w in will be equal to minus H 2 minus H 1. Why negative? Because we have discussed about the sign convention. So, this is 1 minus Q out by Q in. So, this is nothing but you know we can write, I mean if the processes are reversible processes, then it can be written 1 minus. So, in the context of this particular cycle we can write Q out. So, T 4 equal to T 1, we can see from the T S diagram. So, we can write, so this is 1 minus T L by T H. So, you can understand this amount of heat which is added to the system at a temperature that is the maximum temperature in the cycle, that is TH. So, that is the TH. So, this amount of heat which is added to the cycle in the boiler, that is at a temperature TH, and this is the amount of heat which is rejected from the system at a temperature that is TL, that is the condenser temperature. Now, in many books you will find that perhaps if we reduce the temperature of the lower part of the cycle, that means if we reduce TL, then perhaps efficiency will increase, or if we increase TH, also efficiency will increase. So, for a fixed TL, if we increase TH, that means we need to have the temperature, higher temperature of the high temperature part of this cycle at which heat is added to the system. If we can ensure that, efficiency will increase. What is happening? We will be discussing soon that this TL, I mean we cannot reduce beyond a particular value. If you would like to increase TH, then you know that there are many other issues. So, basically we need to, by having some suitably designing the combustion process, we can increase the temperature at which heat is added to the system. But again we cannot increase TH beyond a particular value, and that is restricted by the metallurgical consideration of the metallurgical consideration of several components which are there in the power plant. So, this is TL minus TH, and you know that this TL is basically T4, 1 in the context of this cycle, and that is T3, 2, T3 or T2 prime. So, this is very important. So, let me write it. So, this is T4, 1 because this is either T4 or T1, because you know that this temperature is simple compressible pure substance. So, you know during phase change temperature remain constant. So, the process can be also approximated by the isothermal process, that is what we have seen in the context of the Carnot cycle. So, in the context of the Carnot cycle, this amount of heat which was rejected at a constant temperature. So, T4 equal to T1. Now, in this particular case, though it is constant pressure heat rejection, but as long as the we are working inside the vapor dome, that is isothermal, basically there is no change in temperature. So, basically the phase change occurs at a constant temperature. So, T4 equal to T1. So, you know this is T4 equal to T1, but can I write TH equal to T3 or T2? No. So, basically this is neither T3 nor T2, right. So, this is T average. So, basically this is T maximum average, or you can write T mean. So, what is the conclusion? We can write eta Carnot, that is 1 minus T4 by T3, that is what we have seen. But for the eta Rankine equal to 1 minus T4 by T mean. So, since T mean is less than T3, so try to understand the mean temperature at which this amount of heat is added to this cycle is less than the temperature at which it is added to the Carnot cycle. If this mean temperature becomes lesser, then definitely you can understand that efficiency will be less. So, this is what is the reason why this T mean is less than T3, because this is the Carnot cycle. You can understand from the TS diagram, you cannot write this is as the T3, because this is this lowers part, I mean this particular segment lowers the temperature at which it is added. So, it is because of this reason this T mean for the Rankine is less than T3 for the Carnot, and it is because of this reason since the average temperature at which heat is added to the cycle for the Rankine cycle is lesser than the temperature at which heat is added in the Carnot cycle. Since the average temperature at which heat is added to the cycle for the Rankine cycle is lesser than the temperature at which heat is added in the Carnot cycle, right, efficiency of the ideal simple Rankine cycle becomes lesser than the efficiency of the ideal Carnot cycle. This is not the complete sentence. I have to add something. When both cycles are operating between the same boiling and condensation temperature. So, this is the complete sentence. So, if you would like to have comparison between two cycles, we must secure a common basis for this comparison. So, you can see that if two cycles are allowed to operate between the same boiling and condensation temperatures, then only the efficiency of the ideal simple Rankine cycle will be lesser than the ideal Carnot cycle. And this is quite obvious that you can see. Let me just discuss about. So, now you can understand that so this is, let me draw here. So, this is Ts. So, we have one particular process. So, this is the process 2 to 3, right, and so this is the maximum temperature, this is the, so this is T3, this is T2 and this is S2 and this is S3. So, this is S. Now, what would be average? Average, so this is the average temperature or mean temperature. So, this is T mean. So, you know that let me erase it. We can write this T mean using different with another color. So, I can use this color. So, suppose this is the T mean such that area, say this is 2, 2 prime, 3 prime. So, area, this 2 area, I mean this 2 area of these 2 portions being equal. So, you can understand if we consider the Carnot cycle. So, this say this is the Carnot cycle, right. Say this is S2, this is S3, right. So, this is the Carnot cycle, and what you can see, so this is S and this is T, and this is the temperature T3 at which heat is supplied, and say this is the temperature T2 at which sorry T1. So, this is T1, this is T1. So, this is T1 comma 4, T3 comma 2. So, this is the Carnot cycle. So, this is the Rankine cycle. Now, if we try to superimpose the average temperature at which heat is added over there, so you can understand heat is added at T3. So, T3 comma 2 is T max, T1 comma 4 that is T min. So, this is basically W net. So, this is W net what we have seen for the Carnot cycle. Now, higher the W net, higher will be the efficiency for a given heat input. What you can see, these two cycles are operating between same boiler temperature and condensation temperature, but the temperature at which heat is added to the Rankine cycle is now less than that T3, 2. So, if we try to superimpose, say I am using this color. So, now this is somehow the T average. So, this is T min. So, this is T min. So, what will happen, the W net for the Rankine cycle will be, this is the portion, provided the temperature at which heat is rejected is remaining same. So, that is why I have written that if the boiler is operating, if the power plant is operating between same boiler and condensation temperature, that is for both the cases the temperature at which heat is rejected is remaining same, but in one case it is added to the cycle which is at T3, 2, that is the T max. In other case, though the boiler temperature is remaining same, but this lower segment at which it is added to the cycle, I mean this particular segment at which it is added to the cycle lowers the average temperature, and this becomes the T min. You can see if it becomes the T min as if the heat is added at this average temperature and it lowers the W net. Since W net, that this net work output from the cycle becomes less, we can expect that the efficiency will be less. So, this is the concept of average temperature. So, concept of the mean temperature. So, concept of the mean temperature. Right. So, the concept of mean temperature is important if we try to analyze why the efficiency of the ideal Rankine cycle is less than the efficiency of the ideal Carnot cycle. Okay. So, this is very important. Question is why the efficiency of ideal Rankine cycle is less than the efficiency of ideal Carnot cycle. So, to address this question, we need to understand one important concept, and that is the concept of the mean temperature, right. So, to address this question, we need to understand the concept of mean temperature at which heat is added to the system. Okay. So, what is the conclusion? Conclusion is, if we go back to the previous slide, heat addition at constant pressure. So, you know that if we try to mimic all the processes by using this Rankine cycle, the problem or other problems which are there in a Carnot cycle are not there in this particular case, but the constant pressure heat addition, the process of constant pressure heat addition lowers the temperature, and the temperature at which heat is added to the system, and the concept of mean temperature is coming into the picture, and it is because of this particular segment of heat addition to the system we need to go for this concept of mean temperature, and we have seen that it reduces the efficiency of the cycle. Okay. So, now question is, having established or having understood that the efficiency of the ideal Rankine cycle is less than the efficiency of the ideal Carnot cycle, that is quite obvious, because Carnot cycle is the ideal cycle. We have discussed that we have studied this particular cycle only to understand that the actual cycle, the effort should be given to for the betterment, for the improvement of the actual cycles, essentially to achieve the efficiency of the ideal Rankine cycle. It is not possible at all to achieve the efficiency of the ideal cycle, but objective should be to reach as closer as the efficiency of the ideal cycle. So, you know that in this particular Rankine cycle, at least we can understand that efficiency becomes really less, though we can really address several issues like design of compressor which will handle two phase mixture, it consumes high amount of power, partial condensation at point, designing a condenser which will allowed to have partial condensation, it is also an important issue. So, the problem associated with the Carnot cycle can be eliminated by using this Rankine cycle. That means, if we design the power plant to operate following this Rankine cycle, but at the same time we can see maybe we can address all those issues, but we are also going to invite another problem, that is efficiency becomes really less. So, effort should be taken to address this particular aspect, so that we can increase the efficiency of the Rankine cycle to make it more practical, so that I mean it is, though it is not possible to get efficiency of the ideal Carnot cycle, but at least we can increase the efficiency of the ideal Rankine cycle. So, if we try to address that design modification, of the Rankine cycle. So, there are avenues by which efficiency of the Rankine cycle can be increased by modifying the system. Number one is by modifying the system in several ways. Number one is reducing the condenser pressure. We will discuss one by one. Let me first write what are the avenues. Number 2 is increasing the boiler pressure. Number 3 is superheating the steam beyond 0.3. At least this is the point we have discussed, that one important flexibility of the Rankine cycle is, you know, that we even we can go superheating the steam up to any particular state beyond 0.3. So, it is not mandatory that steam will be taken to the turbine at the saturated state, rather we can superheat the steam beyond 0.3, right. If we superheat the steam beyond 0.3 without going into further analysis, you can just imagine that if we try to superheat the steam beyond 0.3, say up to 3 prime. So, if we superheat up to this point, you can see that this additional amount of W net we can get. So, probably when we have discussed about the advantageous feature of the Rankine cycle, one of the features is that we can superheat the steam beyond 0.3. If we can superheat the steam, at least we can see that we will be getting this amount of additional work output. If we are getting this amount of additional work output, probably we can increase the efficiency of the cycle. But we need to go for the analysis to get this amount of W net. We also need to compromise the heat rejection. So, you can understand, maybe we are getting this amount of work, this amount of W net more, but we are also going to compromise some amount of heat rejection. So, at the cost of getting this amount of W net, we are having some amount of heat rejection. So, we need to go for a detailed discussion whether this W net is relatively higher than this amount of heat rejection. If that is the case, then definitely we can increase the efficiency of the cycle. Not only that, also important point is that if we can superheat steam beyond 0.3, that is up to 3 prime, the quality of the steam at the exit of the turbine becomes, good. So, basically you know that the 4 prime point, 4 prime is closer to the saturated vapor line. So, the point, if the point becomes closer to the saturated vapor line, quality will increase. So, by superheating steam beyond 0.3, not only we are getting this amount of W net, and I am telling you that this amount of W net is even, the relative increment of W net is higher as compared to this heat rejection, though heat rejection amount will increase, but the relative increase in W net will be high, and the resultant effect will be the increase in efficiency of the Rankine cycle. On the top of that, the most important feature that we can see is that we can increase the quality of the steam at the exit of the turbine. So, the expected deterioration of the turbine blades due to pitting and erosion can also be prevented. So, this is one of the reason by which we can increase the efficiency of the Rankine cycle. So, reducing the condenser pressure, increasing the boiler pressure and superheating the steam. Just I would like to discuss only one today, that is reducing the condenser pressure. We will discuss all these three, so one by one. So, let us first discuss about the reduction in the condenser pressure. So, quickly draw the TS diagram. So, this is 1, this point is 2, this is 2 prime, this is 3, this is 4, right. So, this is the TS diagram. So, so, this is the issue. So, we are looking at the possible way by how we can increase the efficiency of the ideal Rankine cycle. One of the possible ways is the reduction in the condenser pressure. So, this is the simple Rankine cycle 1, 2, 3, 4. Now, what will happen if we reduce the condenser pressure? Say we are reducing the condenser pressure up to this particular point. So, this is the P condenser new. So, this is P condenser new, and let me complete it quickly. So, this is the P boiler and this is old. So, this is the P condenser old and this is the P condenser new. So, now what we can see, if we reduce the condenser pressure, we will discuss now what we can see. So, this is 1 prime, this is 4 prime, this is 2 prime, 2 double prime. So, 1, if we reduce the condenser pressure, cycle becomes 1 prime, 2 double prime, 2 prime, 3, 4 prime, 1 prime. So, this is the cycle. The previous cycle is 1, 2, 2 prime, 3, 3 and 4, 3, 4, 1. So, what we can see, if we lower the condenser pressure, you know that we are going to have this much amount of additional work, right. The TS diagram is very important, because again I am telling, by drawing the process line in TS plane, just we can say that this is the W net, because W net is equal to Q out minus Q in minus Q out. So, this is basically, this is the Q out. So, this is the area that is Q out. So, whatever may be the Q in, because if we reduce the condenser pressure, you can see that I mean Q in will increase definitely, because Q in will increase by this area, right. So, Q in will increase by the area that is 1 2 double prime 2 1 1 double prime. So, though this amount of q in is increasing, but we are going to get W net. So, this W net, so this delta W net is higher than delta W q in. So, if we reduce the boiler, if we reduce the condenser pressure, we can see that we are going to have slight increase in q in, that is delta q in, but that increment is not large as compared to the increment in the W net. In other way, the increment of W net is more than the increase in q in. So, the resultant effect will be the increase in the efficiency of the Rankine cycle. So, again I am telling, if we lower the condenser pressure, we can see that though there will be slight increase in q in, but that increment in q in is insignificant as compared to the W net or increment in W net that we are getting. So, this is basically delta W net. Okay. So, the resultant effect will be the increase in efficiency of the Rankine cycle. Fine. So, we can increase the efficiency of the Rankine cycle by lowering the condenser pressure, that we can see. So, by lowering the condenser pressure, we can increase the efficiency of the Rankine cycle. So, let me write over here, by lowering the condenser pressure, the efficiency of the can be increased. So, though it is there that we can increase the efficiency, the problem is, if you look at carefully this TS plane, now the exit state of the steam, state of the steam at the exit of the turbine is 4 prime. So, the quality of the steam at the exit of the turbine deteriorates. So, if we reduce the condenser pressure, the efficiency of the cycle will increase, but we can see from the TS plane is that the quality of the steam at the exit of the turbine will be poor. So, the chances of having turbine blade erosion will be there. Not only that, another important problem which is associated by lowering the condenser pressure is that you try to understand. So, increase, but the steam quality at the turbine exit will reduce. So, the chances of turbine blade erosion will be there. What is the main problem? See, now if we reduce the turbine pressure, condenser pressure, which is also known as the turbine back pressure. So, the pressure at the exit, pressure of steam at the exit of the turbine is also known as the turbine back pressure. So, if we reduce the condenser pressure, we cannot reduce turbine, we cannot reduce condenser pressure drastically, because if we reduce the condenser pressure drastically and if it becomes less than the atmospheric pressure, then there will be leakage of air from the surroundings into the condenser, and that air will try to have mechanical problem with the pipe through which coolant is circulated. So, if we reduce the, we cannot reduce condenser pressure drastically. If we reduce the condenser pressure and if it goes beyond the atmospheric pressure, condensers are normally operated below atmospheric pressure, but we cannot decrease I mean we cannot operate condenser at a pressure difference which is very high. Pressure difference, that is pressure at which condenser is operating and the atmospheric pressure. So, if the condenser pressure becomes very less than the atmospheric pressure, then chances of air leakage from surroundings to the condenser will be very high, and that air will create mechanical problem in terms of the coolant which is circulated through the pipe. Not only that, that air will try to reduce the heat transfer coefficient. Okay. Also, another important point that I would like to mention, that you know that the condenser pressure, whether we would like to operate at a sufficient below the atmospheric pressure or not, that will be dictated by the temperature of the water which is available near the plant site, because this is the pressure. So, this is the saturation pressure corresponding to the temperature of water which is available at the plant site. So, based on the temperature of the coolant which is available near the plant site, the condenser pressure should be decided. Okay. So, the summary of today's discussion is, we have discussed about the concept of mean temperature, and we have seen that by invoking the concept of mean temperature, we could explain why the efficiency of the ideal simple Rankine cycle is lesser than the efficiency of the ideal Carnot cycle. Then we have discussed about a few possible ways by which we can increase the efficiency of the ideal simple Rankine cycle, and we also have discussed and one of the three important ways, that is by lowering the condenser pressure. If we reduce the condenser pressure or if we lower the condenser pressure, we can see that the efficiency of the plant efficiency of the cycle can be increased, but at the cost of that increase in efficiency, we need to compromise the quality of steam at the exit of the turbine. So, we need to have a judicial balance between these two. Not only that, we also have discussed about critical issues about the selection of the condenser pressure in the context of the operation of the steam power plant. So, with this I stop here today, and in the next class we shall discuss about the remaining two points, that is by increasing the boiler pressure and superheating the steam beyond 0.3. Thank you very much.